Good morning, good afternoon, and good evening to all of you in the air. It's nice to see you all in the air. And welcome to Master Forum in Sustainability, a science organized by Future Earth Global Secretariat at Taipei. And it's our great pleasure and honor to have a 2021 Physics Nobel laureate, Dr. Klaus Hasselmann, to share with us his groundbreaking works and fascinating research career. Before beginning Dr. Hasselmann's talk, I would like to invite the Vice President of Academia Sinica, Dr. Mei Zhou, to give opening remarks. Dr. Zhou, please.
Yeah. Okay, can you hear me okay?
Yes, very clear.
Yes, okay. And good morning and good evening, maybe good afternoon. Our honorable guest, Dr. Klaus Hasselmann, and special guests, ladies and gentlemen. On behalf of Academia Sinica, I'm delighted to welcome you to the Master Forum in Sustainability Science. Meet Dr. Klaus Hasselmann, the 2021 Physics Nobel laureate. Dr. Hasselmann has made important contributions to climate science that is a key element in support of global sustainability transformation. Sustainability improves the quality of lives, protects our ecosystem, and preserves natural resources for future generations. Academia Sinica strongly supports the development of sustainability sciences and believes that this is the key to a better future. We, as global citizens, have seen recent warming climates and related natural disasters, such as record-breaking heat waves and extreme hazardous rainfalls in many regions on Earth. The scale of recent global climate changes is unprecedented over multi-centuries to many thousands of years. Dr. Hasselmann is the pioneer to point out that this unequivocal human influence on the climate system. Over 40 years, Dr. Hasselmann's model for identifying natural phenomena versus human activity signals have greatly improved our understanding of climate variability and how to connect changeable and chaotic weather to climate. His work has provided the essential foundation to prove that global warming is due to anthropogenic greenhouse gas emission. So this forum is organized by Future Earth Global Secretaries Hub Taipei and co-organized by Taipei Representative Office in Hamburg, Germany, Center for Sustainability Science at Academia Sinica, Future Earth Taipei, Future Earth Global Secretary Hub of Japan, China, and South Asia. We are greatly honored to have special guests from different parts of Asia to share their insights and talk with Dr. Hasselmann today. This forum, I believe, will inspire every participant today and have a deeper and better understanding of the foundation for modern climate science. Therefore, I would like to welcome you again and wish you a successful forum. And thank you, Dr. Hasselmann. It is our honor to have you join us. Thank you.
Thank you, Vice President Joe, for your opening remarks. Next is the focus of today's activity. It's a speech by Dr. Hasselmann. Dr. Hasselmann is a critical oceanographer, a climate dynamicist. His works cover turbulence, nonlinear interaction of oceanic waves, stochastic climate modeling, fingerprint method, integrated assessment studies, and even unified field theory. Dr. Hasselmann was the founding director of Max Planck Institute for Meteorology, science director of DKRZ, German Climate Computer Center, and the co-founder of European Climate Forum, now named Global Climate Forum. Now let me invite Dr. Hasselmann to give his talk. Dr. Hasselmann, the air is yours in the next 25 minutes, please.
Thank you, and my greetings to the other side of the world globe. I'm still fascinated about being able to talk and look at people so far away. This makes the Earth think, and people get to know each other much better, which I hope brings more peace for all people. Our Christmas celebration, which is coming now, is exactly the celebration of peace for which we all pray. So thank you for the invitation and your interest in my work. I'm very happy to talk about my scientific findings and personal experiences during my career. However, we shouldn't forget we are currently plundering our natural resources. For example, if we continue to burn the available fossil fuels, we'll heat the Earth by 5 degrees. And there we are in the middle of the subject we are dealing with today. However, before I talk about my work, which led to the perception of the Nobel Prize, let me say something about my background and how I got into climate research. My family had to flee from the Nazis in the 1930s, and I grew up in England. It was a very different time. There was no television, no cell phones, no computers, and we played on roads with hardly any traffic. We played a lot of sports, and when we didn't know what to do, we went into the nearby forest, made campfires, fried potatoes, and climbed trees, and explored our surroundings. And we built trolleys and rushed down the hills with them. As you can see, it was a childhood dream full of curiosity and fantasies. That's a pretty dark, Many children in rich countries today are confronted with endless, often useless input from a broad spectrum of media. Most of the toys nowadays are prefabricated. My impression is, for us, it's much easier to develop strong early interests. For me, these were the inspiration of my career. Always wanted to discover how the world works. When I built my first crystal detector and heard voices from far away, I felt like the greatest explorer. It was a great feeling. I did that on my own. I quickly developed an interest in physics, which I studied eventually after graduating from high school. Now you want to know something about my research. I was always driven by pure curiosity. Therefore, I've been working in many different fields. When I was young, I attempted to solve the turbulence problem, but that was too ambitious. It has not been solved today. Moreover, the outcome was my interest in the missing link in the development of ocean surface waves. How small ocean waves developed into longer waves. I did this a little bit from other colleagues. It was clear that one important term had been missing in the computation of the nonlinear cross-spectral energy transfer. I developed an equation including the transfer energy from the peak of the wave spectrum towards lower and higher frequencies. This was described by a 6-dimensional Boltzmann integral and was verified in an experiment, John Swap, the North Sea Wave Project, later in 1969 in the North Sea. The figure, this figure, this is a 50 bit. The figure shows the source terms of the energy balance equation with the input of the wind spectrum, with all wind input enhancing the peak of the spectrum, a low dissipation field SDS by wave breaking, and the non-energy transfer SNL. The result is shown in this figure as a set of directionally integrated frequency wave spectra, which are measured on the line at an angle of 90 degrees to the coastline. The peak is enhanced by the wind input and is shifted to low frequencies by the nonlinear wave-wave interactions. I was able to use this technique for seismic waves and planetary waves, and then also the idea to develop a new particle theory, adding to the 4 space-time dimensions 8 additional wave dimensions, thereby connecting Einstein's special and general relativity theory with my theory. However, this remained a hobby for me, and the physicists did not like a meteorologist moving into the field. My search for meteor lakes led to a global wave forecasting model, which was developed by my wife and is running now in many forecasting centers around the world. The model is used for shipbuilding, building ocean platforms, and for coastal protection. Surfers also greatly appreciate the global wave forecast this enables. This research also included investigations of AC2 islands, which led to the question whether short-term weather fluctuations can trigger long-term climate changes. That leads me into the midst of climate research. Syukuro Manabe, with whom I share the Nobel Prize, developed a model of the radiation balance between the sun and the Earth. See here in the picture. The radiation of the sun heats the surface of the Earth and is then emitted as infrared radiation. Water vapor and some trace gases, notably CO2, are effective in absorbing this radiation from Earth's surface before it escapes to space. While these greenhouse gases ultimately re-emit the energy they absorb, not all of it goes in the right direction. Some is emitted back towards the surface. This is what we call the greenhouse effect. Without this natural greenhouse effect, the temperature on the Earth would be around 30 degrees warmer. 30 degrees colder, which would, for example, cause the oceans to freeze. This was shown by Syukuro Manabe already in the 1960s. But climate is not only a system driven by radiation. As you can see in this illustration, climate is also an issue of oceanography, glaciology, carbon cycle, and many other components of the Earth system. When I started the Max Planck Institute of Meteorology in 1975, this was shortly after the Club of Rome had published its first warnings that mankind was destroying the planet. We all read the book with great interest, and my scientific curiosity was stimulated. Our friend David Keeling had already started in 1960 to measure CO2 from Mauna Loa mountain on the island of Hawaii, the largest of the Hawaiian Islands. The site was free from disturbing aerosols. At first, nobody took him seriously, but later this curve became the standard reference curve for model computation. When I began my climate research, everybody thought I would immediately buy a big computer. However, I first wanted to understand the basic theoretical principles of climate change. My first climate paper on the subject was the stochastic climate model, which provided an insight into the formation of long-term internal variations excited by short-term random weather fluctuations. It was found that the short-term weather fluctuations can trigger longer-term climate variations. Well, that was all over 40 years ago. A colleague of mine, Giorgio, found a nice picture for this phenomenon. If you throw constantly tennis balls against a big, heavy medicine ball, nothing will happen for some time. However, eventually the big ball will start to move. The tennis balls are the weather, and the big ball is the ocean. Thus, the ocean is in effect the long-term memory of climate, besides ice sheets and the biosphere. Thus, I describe weather and climate in terms of two timescales: short-term stochastic or stationary fluctuations, represented by a wide spectrum, which is associated with weather, and timescales of days and weeks, and long-term variations of years up to millennia and more, representing climate variations. The term of variability in this context is referred to as noise. Thus, we look for the detection of so-called signals which cannot be explained by eternal variability, and in case of success, compare the signal with the expected changes due to different forces. If the similarity is sufficiently good, we attribute the signal to these external factors. The idea was first to define the noise from data or extended model simulations, and to construct the expected responses or guesses of fingerprints to the possible forcing factors. Following up this work, we very soon found that adding additional greenhouse gases to the natural ring of natural ring of aerosols in the atmosphere will heat up the Earth. This means the measured increase in mean temperature was caused by mankind. For this work, I received the Nobel Prize. I will not go into more details here because some of you will not be familiar with the techniques. However, it led to a paper published in 1996, in which I presented the proof that with a probability of 95%, the increase of the global mean temperature was man-made. We know now that the global mean temperature has already increased by 3 degrees centigrade. No, sorry, by 1 degree centigrade. No, not one that bad. If we are aiming at 1.5 degrees, we must do a lot. We have to do it immediately. Models predict that we'll end up with 2.5 degrees warming. Our efforts are not extended and increased, but our actions are increased. A further important task was to communicate the results of our research to the public. This really became a problem. I was not good in communicating with the press or the public, and I thought I should rather use my time and talent concentrating on research. The two of my colleagues, Mujib Latif and Hamid Gasser, took over this task most effectively, became well known as a popular link between the climate research, the press, and the public, but at the same time still contributing essentially to research. The public found the information interesting, but there was no adequate political reaction. People are not made to think in long terms. Nevertheless, I wanted to use my scientific knowledge to show politicians and decision makers with which means they could most effectively prevent climate change. I'd always been interested in economics. I developed coupled climate and economic models with my wife and later Dmitry Kovalevsky. Important aspects of the models, in my view, were the dynamical and multi-timescale nature of the system, both in natural science and the human parts. My view was the inherent uncertainty of all model components caused the development of models as statistical optimization models. Model results were important to guide climate-related policymaking, despite the inherent uncertainties of the models. It has now been 50 years since the Club of Rome published its first warnings about environmental change by mankind. And we climate researchers have been warning for the last 40 years, proving scientifically that climate change is real. The IPCC combined all climate research results already in its report in the early 1990s and received the Nobel Prize in 2008. However, not enough has happened to stop global warming. We have continued to collect multiple scientific evidence that humankind is responsible for global warming that is unprecedented in our history. Our knowledge has never been more comprehensive than today. Unfortunately, our willingness to react has not increased accordingly. We're already in the midst of global warming. We've already experienced multiple consequences of climate change: heat waves, melting of inland glaciers and polar ice caps, rising sea levels, floods, droughts, and loss of biodiversity. Today's challenge is to transform scientific knowledge into political and societal action. This is a task for every individual on Earth, but mainly in the rich part of the world. We are the ones who caused global warming in the first place. We are responsible for most of the cumulative CO2 emissions. Yes. Secondly, it is a task for politicians. They have set up rules and regulations to limit greenhouse gas emissions. They have to pave the way for the development of the poor part of the world without increasing the use of fossil fuels the way the industrial countries have done before. And last but not least, mitigating climate change is a task for scientists. We need to make the causes and consequences of global warming as understandable as possible. We need to describe paths and ways to limit CO2 emissions to net zero by 2050. A young girl of 15 had to place herself in front of the Swedish Parliament on the 24th of August in 2018 with a sign saying, "Stochastic för klimatet." This was the starting point of the workable worldwide movement, Fridays for Future. In the last years, they have found a way to stir up the public and voters more than we scientists have been able to. Thank you, Greta. I, for my part, can only repeat my urgent message to all decision makers worldwide. The longer we wait, the more expensive the necessary transformation will be. In addition, the cost of damage caused by extreme weather conditions, pandemic diseases, and global mass migration will only increase with time. We cannot wait. Thank you.
Okay. Thank you, Dr. Hasselmann, for the insightful and intriguing talk. Our next session is our discussion session. We have three panelists today. Dr. Masahide Kimoto, President of National Institute for Environmental Studies, NIST, an expert in climate modeling, variability, and predictability. And Dr. Danya Xu, Chief Scientist from Southern Marine Sciences and Engineering Guangdong Laboratory, an expert in oceanic modeling and focus. And Dr. Miguel, Associate Professor, Department of Atmospheric Sciences, National Taiwan University, an expert in atmosphere-land interaction. We'll begin with the first round of Q&A. So I would ask each panelist to ask a question in the first round. And if time allows, we can have a second round of Q&A. So let's begin with our discussion. Dr. Kimoto, would you like to begin to ask your questions?
Okay, thank you very much. And first of all, congratulations and the biggest appreciation to your Nobel Prize winning, Dr. Hasselmann. And thank you very much for joining us to give your excellent lecture. And I would like to ask a question, but before that, I would like to appreciate your achievement, especially I think you're basically a theoretical scientist. And your first theory of stochastic climate model, that's noisy weather can hit constantly the ocean and then excite very slow motion in the ocean. And that led to the discovery of decadal climate variability, namely very slow tens to several tens of years of the fluctuation in the climate system. At that time, maybe more than 40 years ago, we didn't know anything. We didn't even know the existence of El Nino, but you predicted that constant white noise of the atmosphere can bring the decadal prediction. And that nowadays led for us to issue the decadal prediction of the climate. And other one is that among these internal variability, it is very difficult to detect subtle climate change signal, but you have made a theoretical consideration and you showed the way to systematically extract the small signal. And in these theoretical consideration, I think that climate models, numerical models of the climate, may be helping to prove your theories. And I would like to ask you, from your theoretical point of view, what is the role of computer models of climate in climate science and climate change problem? That's my question.
Well, the climate system is so complex with so many degrees of freedom that it can only be treated in detailed with numerical models. So I think the computer is an essential ingredient to understand climate change. You can develop some general theories of what's happening, but to really come up with quantitative numbers, you need a computer to translate these ideas into a computational model. So computers are essential for climate research.
So you try to promote computer model development and simulations in your leadership of the Max Planck Institute?
Yes, I think when the institute was created, my first condition was that we obtain a large computer. Otherwise, we could not carry out the detailed computations that are needed to understand the complexity of the climate system.
Okay, thank you very much.
Okay, thank you for the question and the answers. We tried. So this question would be asked Dr. Xu to ask your questions.
Okay. Hello, Dr. Hasselmann. Thanks for your excellent speech and congratulations again for you to win the Nobel Prize. And it's my great honor to be a special guest. And I would like to ask you a question about climate change. Actually, I would like to follow Dr. Kimoto's question. Okay, now we have a much better understanding of global warming because of your seminal works, which developed a stochastic model that linked weather and climate together, simplify the climate system into short-term and long-term variations. Such simplification of complex systems is very important in understanding climate variability or any other complex science problems. Even economies cycles can be, distinguished into two noise and signal, such kind of things. Well, my question is, in order to make sure the climate models can deliver reliable predictions, what aspect of the numerical models can be improved in developing the next generation of the Earth system models? Since I'm myself is an ocean modeler, so I would like to know your comments on the next generation of the, new kind of the ocean models or Earth system models. Thank you.
Well, I think we have a very good ocean atmosphere model already today, so I'm not really involved in the details of the current modeling to say what the best ocean atmosphere model is. But I think the basic question we have today is to understand the interaction between the ocean atmosphere system and human activities on the economic field, in the economic area. So I think the main focus of research should now be the interaction between human society and the natural climate system. I think there are many open questions that we still have to study there.
Yes, thank you. Just like, before IPCC groups, group 1 and group 3 people, they don't talk each other, but now they're working together to, develop the new generation of the new kind of a system model, which includes the human activity and social economies. But I think since I'm a physical oceanographer, I don't quite understand of how difficult to integrate this kind of social science into the natural science into the models. I'm not sure if you can give some comments on this kind of parameterization, or I don't know. Solve the yeah.
Well, I agree. It's a big challenge and a difficult task, but it's a lot of fun to interact with economics and to try to translate their ideas into an economic model and to be able to explain to the economists how the model works. And so the interaction between different disciplines, I think, is very essential to make progress in this area. So I think one should not be discouraged by difficulty of communicating with people from different disciplines, but just be very patient and try to understand their way of thinking and find ways of developing models which express the ideas that both of us have, of both fields.
Definitely. Thank you very much. Thank you.
Okay. Thank you. Thank you for question and answer. Dr. Miguero, would you like to ask your questions?
Sure. Thank you, Dr. Hasselmann, for your time with us and sharing your thoughts. That's very nice. So I actually also want to follow previous question about this, how to integrate this social economy behavior or modules into the models. So my background is more on the land surface modeling perspective. And because a lot of human activities, so for example, like urbanization or agriculture, irrigation, so stuff, then need to be integrated in the model. So sometimes in probably about 10 years ago, when the land model community, they talk about this so-called IAM. So it seems like try to embed this social behavior into the models. But in the beginning, I thought it's only one way. But actually, when I saw your slides, you have from the social economy to the economy model, and then it actually can feed back to the social economy model again. So I'm wondering, maybe the next step is possible to have this two-way interaction at the same time, or that might be another, I don't know, different story. Yeah, just want to have some of your comments on this. Thank you.
I think it will be a very different story. Unfortunately, I'm rather old right now, so I'm not the right person probably to bring this across. But the whole question of the interaction between the scientific community and the economic community and the socio-economic community, I think, is a very important aspect of this whole question. So the development of the right models and the right way of looking at this problem, I think, is a very important problem. But I'm afraid it's a problem for the next generation, not myself. I'm rather too old and too old-fashioned to really contribute too much. But I'm very happy to hear that younger people are pursuing this problem, which I think is very important. And I think the ability to solve the problem will be very important if we want to solve the climate problem and the economic problem simultaneously. So I really encourage young people to pursue this way of research.
Thank you.
It looks like we need to expand into not just Earth system model. It's like an anthropogenic Earth system model now. That's probably for the next round of model development. So we still have time, so we can start our second round of Q&A. Dr. Kimoto, would you like to ask another question?
Okay. Yes, I happen to be involved with decadal variability and decadal prediction. And I have acquaintance with so many German scientists. And everybody talks about the Hasselmann theory. And now your prediction, 1976, is proven. Recently, there is a very nice review of a decadal variability. And as for the triggering mechanism, your theory still is the mainstream of the current understanding. Congratulations. But my next question is something different from the research topic itself. Or more of, I'd like to ask you about how you try to raise your followers or your colleagues as a director of the Max Planck Institute, because the climate science is becoming more and more societally relevant. Therefore, climate scientists have to respond to the societal needs but at the same time, it's a science. Therefore, it should be basically curiosity driven. And I understand that the Max Planck Institute is one of the biggest institutions which has the duty of responding to the societal needs. But in order to respond to the societal needs, you have to have the basic high standard of science. As the director, as a leader of such a big institution, how do you manage to deal with scientists, their scientific interest and societal needs, and then more of an obligation type of things?
The important thing as a director is to recognize that you have good colleagues you can work together with and recognize where your own limitations are. And my limitations are really communicating effectively with the public. I tend to stutter a lot and to forget what I was going to say and so forth. But I have two colleagues that are very good at this. One is Mujib Latif and the other is Hartmut Grassel. And these two enjoy talking to the public and the media, and they're always attracted by the media. And so you find these people everywhere in Germany talking to the public about the problems of climate. And so these are people that are excellent at doing this. And I was just very fortunate at having two colleagues who enjoy doing this and do it very well. And so I was happy to let them carry this over, and I just sit back and let them carry over. So I was just very fortunate.
You're so hesitant, but I think that you can recognize what you can do and what you may not be able, but to try to judge, people's talent and try to make maximum use of those things, and the balance between the scientific interest or the public relation and all these things. That's based on your recognition, high standard of recognition. I can learn very much from your experience and attitude. Thank you very much.
Yeah, I guess it's very important to allow enough room for the younger generation of scientists or researchers to develop themselves. Okay, so Dr. Shi, you want to ask your next round of questions?
You're muted.
You're muted. Dr. Shi, we cannot hear you.
Okay, sorry. Okay, it's my lucky day. I can ask another question. Dr. Hasselmann, yes, it seems, for scientist community already provide very comprehensive, very solid conclusion about the climate change. Global warming is a truth, and it is true. And but for the different governments, it's really hard to get a very satisfied agreement, just like a Paris Agreement or something. This is understandable because for the economic development, this is going to have the different country have the different energy policy and to maintain their economic growth. But do you think, for scientists, do you think the geoengineering is the way to mitigate the global warming? Is that works? Since I know a few years ago, 10 years ago, for the oceanographers, they have some kind of ion experiment. They put ion into the high nutrient, low chlorophyll region and excites the bloom, and which can be fix some biology pump can fix some carbon dioxide. So do you think geoengineering is a way to mitigate the global warming, just like put some air source or space to reflect the sunshine, such kind of thing? What do you think?
think geoengineering can help, but I don't think it is essential. I think we have the economic abilities nowadays to switch to environmental friendly ways of producing energy and standard of living without having to resort to these other techniques. So I think we're not dependent on geoengineering. I think we can simply switch to alternative energies, which right now are competitive with the fossil fuels. And if we see that this is the way forward and have some minor economic stimulus to develop these techniques, I think that we can solve our problems in the future. But there, I'm optimistic. There are other people that are more pessimistic than I am. They're also good experts, but I myself have the more optimistic point of view that we can actually solve the climate problem using the techniques that are available today and are already commercially competitive with the fossil fuel techniques.
Okay, thank you.
Okay, Dr. Miguero, you want to ask another questions?
Sure, thank you. Hi, Dr. Hasselmann. My second question may be more from students' perspective. So sometimes the students wants to know how the researchers came up with these questions or this idea or this topic. So, like for example, a storyline from your early work of this stochastic model for climate variability to the later on for this detection method, the fingerprint methods. So can you share more about these connections from early work of theory and then to develop this fingerprint method to detect this natural and anthropogenic climate changes? This like almost like 30 years from 1970 to 1990s. So this kind of transition or the connections, can you share some more? Thank you.
I'm not sure if I completely understand your question, but I think one of the questions or one of the answers that I have, maybe it's not the right answer to your question, but my answer is I think that the way that people respond to long-term challenges like climate change is a rather slow process. And it's the task of policymakers to develop techniques for actually adapting the economic system to the long-term challenge of climate change. And I think we have the techniques to do this. And the big problem that we have today is that the politicians realize that they now have to implement techniques to translate or transform our economy into one that is long-term viable with the climate change challenge that we have. But I think the techniques that we have are available to do this, and I myself am optimistic that with the support of young people, like the Climate Future activities, that we will actually convince the policymakers and the economy to respond to the climate change challenge, and that this can be done in the time that is available. I'm not sure if my answer is the right answer to your question, but I hope that it helps you sometimes.
Okay, maybe I can help a little bit. I guess Dr. Low want to ask, how do you connect your study in your earlier time, like a turbulence or the stochastic model of Earth interaction, and later to a development of fingerprint method? So through your research career, how to connect your early time or very small scale like turbulence study into a global climate study? What's your experience?
I'm not quite sure if I understand the question. The question is my optimism that the long-term climate change problems that we have can be solved with our short-term policy, or what was the?
Probably, I guess, in terms of your personal research experience in earlier time, you studied like a turbulence or the nonlinear wave interaction, relatively small scale, but it's quite nonlinear. So how this kind of experience help you to develop for example, the data stage of this fingerprint method or concept? How do your earlier the research in your early career helps the later development of your most groundbreaking work?
Well, I think the main thing is to have a very broad view of things and not to be narrowed in by your own particular expertise in one particular area of science. I think there are many stimulating insights and ideas that you can develop or learn from other areas. So I think to be open for the ideas that develop in other areas of science, I think is very important as a scientist, so that one should be willing to understand other areas. And I was interested in economics, for example, and the question of interactions of policy and economics in general, with the whole question of how society develops. So I think the whole dynamics of systems as general, I think should open your mind to look at different questions, and then you can see how the expertise that you develop in one particular area can help you solve problems in other areas. So I think it's important that scientists have a sufficiently broad view of things to be able to pick up new ideas from other areas. And I think this was supported also by the Max Planck Society, which has this policy that it has its that this directors should be free to pursue many different areas of research in parallel.
Okay, Dr. Loh, does that respond to your question?
Yes, thank you very much. It is, yes.
Okay, good. Actually, we do get some questions from the online participants. One of the questions is, what can we do to improve climate model in a regional perspective? That seems to be quite urgent. What's your comments on a smaller scale instead of global scale?
The question, I mean,
it's a question. How?
I'm sorry, I didn't quite follow.
The question is, what can we do to improve climate models in a regional perspective? For example, climate change in a relatively small regions.
Well, that's a big challenge of how to develop climate models that both encompassing the global phenomenon as such, but also being able to describe the details of what happens in one particular area, which is what concerns the people that live there. So the question of developing climate models that can couple these different time scales, space scales and time scales, I think is an important challenge for climate modeling. And I think we were very fortunate that while I was developing climate modeling at that time, computers were developing very fast, so we had obtained after some time computers that were able to both resolve the small time scale, small space scales that you need for local people, and also the global scale you need to understand the climate system as a whole. So the coupling of different spatial scales, I think, is very important, and that was possible through the development of computers.
Yeah, so it sounds like we need a very, very huge computer in the future. Yeah, okay. So any of our panelists like to follow up with these similar questions in terms of regional perspective? No? Okay.
Yeah, I think it's downscaling, yeah. High resolution downscaling, since we have the comprehensive global model and we can construct as a regional model, very high resolution, and use the downscaling scale to, predict, to make the regional model better, right? This is my understanding of this.
So,
Yes,
yeah, please, Dr. Hasselmann, you have anything to say?
Well, I think it's quite true. It's very true. The question of the the connection between the global scale model and the local scale model, I think, is a big challenge that we have today, which we can address very well with the computers that we have. So I think we're very fortunate that the advance in technology has made possible to connect the global and the very local scale, which is of course very important because the person living somewhere wants to know what happens to the change in climate in his local area, but that depends very much on what the global scale is happening. So the coupling between the local and the global scale, which is now possible with computers that we have, I think has been an important advance in our global and local climate modeling.
Okay. I'll follow up with the question. Recently, Tim Palmer has a comment on IPCC AR6 WG1 report, and he actually mentioned that 100 kilometer spatial resolution is too close for adaptation or even and to evaluate the vulnerability. So he seemed to suggest we need Earth system model with a spatial region of 1 kilometers. So I'd like to ask your opinion, also the comment from our panelists. How can we achieve that? I mean, Earth system model with 1 kilometer spatial resolution. Any comments?
I'm not a technician and I haven't been doing actual climate modeling in the last few years, so you should maybe ask a younger person who's doing this thing. But I think the question of coupling the very small scale where we live to the large scale climate problem on the global scale, which determines what happens on the very local scale, I think has been the basic challenge of climate modeling since I've been doing this work. So I'm just very happy that the computers have now developed to the point where you can actually couple the very small scale with a very large scale. And I can only wish the next generation much success in the ability to couple the local climate change problems to the large scale global climate scale problem, which I think has always been the basic challenge of climate modeling.
Yeah. I'd like to put a question to Dr. Kimoto. Kimoto-san, you have been developing the climate model for many, many years. So what's your comment on this, the question I just raised?
The global versus regional high resolution?
Just 1 kilometer global model.
Okay. Since the atmosphere and ocean is fluid, therefore the resolution higher the better. So 1 kilometer may not be enough. And this is one direction. But Hasselmann's advocation is that since the climate system is full of internal variability, therefore signal versus noise, this is another dimension of the problem, Hasselmann insisted. Therefore, we have to take balance between the resolution and the ensemble size. In order to say something on the climate science, you need to distinguish noise and the signal. So we have to do it at the same time. If you go to higher resolution, you have to reduce the ensemble size. You go to the big ensemble, then you have to reduce the great resolution. This is a very difficult problem. But one of the hope we can have is that although the larger scale and the smaller scale interact each other, but the direction of interaction is largely from large scale to small scale. That's why regional downscaling can work. Therefore, of course, the 1 kilometer global resolution Earth system model is a nice thing to see, but it may not be the unique solution. to the problem. We may be able to use different technology to fit the problem we would like to answer at this time of day. So I think that we shouldn't forget Dr. Hasselmann's advocation that climate system is full of different large spectra of various modes of fluctuation. And then your signal is my noise, and my signal is your noise. So that's kind of thing.
That's an excellent comment and suggestion. Dr. Hasselmann, we have a question from a PhD student. So the specific question is, what's your advice for a final year PhD student?
I'm not quite sure. You say, what do I advise? What do I advise my student?
No, for the last year, a PhD student, a student who's working on his thesis in the final years. Do you have any comments for those students who's graduating or getting their doctoral degree?
Well, my first advice is to work very hard. And the second advice is to be very open-minded and not to listen only to your professor, but to many other people, and to have a very broad view of your problem, and let yourself be surprised by what you learn. And I think that's the way that I always did my own research, and that's the way I advise my students. Have faith in yourself, but you have to work hard. Without working hard, you won't achieve anything.
Yeah, that's a very good suggestion. Everybody should listen to that. And I have a question. At the end of your talk, you actually mentioned Greta. So actually, there are many criticisms about the Greta's action or advocacy. So what's your comment on that? How should we treat Greta or view their response or their anxieties?
I think Rita has a very right approach to this. First of all, to be fully aware of the fact that we live in a viable environment that we can affect both positively and negatively, and that we should adapt our life accordingly. And that's the first point. And the second point is to realize that we can actually live a very pleasant life without an enormous impact on the climate simply by not wasting resources and living modestly, and that can be a very pleasant life. And so we try to do that ourselves, and not to spend too much unnecessary stuff. And I think if you have this approach to the environment and to the world in which we live, I think we can live a better life without wasting our resourcing.
So another question, are you confident in the possibility in achieving net zero by 2050?
I'm not quite sure that I understand. Am I optimistic that we can achieve these goals, or
how confident you are?
Confident.
How confident I am? I think I'm basically very confident that we can achieve this because we have that technology nowadays. We can actually switch to renewable energy without a great higher cost than the fossil energy. And it's just the willingness the ability to actually do this, be willing to do this. We can do this without additional costs. And once we realize this, and we can achieve this. And I'm very confident that the young people have a good way of communicating this to the public, and that we can actually make use of the technology that we have nowadays to use renewable energy at an affordable cost to solve the problem of climate change. But whether we'll do this or not depends very much on how sensible our politicians are.
Okay, that seems a very good comment. For us to close this forum, I guess it's time to close the forum. Almost an hour now. So our special thanks to Dr. Hasselmann for sharing the fascinating works and ideas with us. And we also like to thank the daughter, Anna Hasselmann, and the Mrs. Hasselmann, Dr. Sudana Hasselmann, for helping organize this activity. So thank you again very much, Dr. Hasselmann, and thank you to, oh yes. So I guess currently we have more than 300 online participants. It seems to have been quite successful forum. And I'd like to thank you to all of you in the air to spending an hour with us. And goodbye. And thank you again. And thank you to everybody. And thank you to our panelists. And thank you to Dr. Hasselmann. Thank you.